Good morning, everybody. Today we will continue with another very nice topic in physics, electromagnetic induction. It is a very useful and important topic because electromagnetic induction, which we call EMF or back EMF, is widely used everywhere in industry. We shortly touched this topic during the electric motors in previous chapters. So what we have within the electromagnetic induction chapter, first of all, we will talk about what the Faraday law tells us to explain the induced EMF. We will talk about this. And we will learn how to get the direction of an induced EMF and induced current within the circuits. Then probably next lecture on Thursday, we will talk about induced electric fields. And then Maxwell equations, which are the four fundamental equations that completely describe both electricity and magnetism. We will talk about this within that chapter. Then finally, we will see some properties of superconductors. They have very nice electrical and magnetic properties, and they are also widely used in industry due to that properties of the superconductors. So here you see two pictures. One is post machine, the other one is alternator within the cars. So what we have within the post machine, here you see a credit card, okay, or bank card, and here you see a black ribbon on the card, this one, okay. So there are more or less three ways to use post machines with the cards. So one way is there is chip on the other side of the card, and you can insert the card into that place, okay, and then you can pay whatever you buy. Another way is that by using that ribbon, black ribbon or magnetic ribbon here on the back side of the card, you can use that method, okay? And the other one is you can just simply touch the card on the surface of the post machine. We deal with the magnetic part today, so black ribbon on the back side of the card. So what is the mechanism? The post machine scans the information that is coded in a magnetic pattern on the back of your card. There's a magnetic pattern, okay? And we have to move the card very quickly, right? If you are using the chip, you just insert and keep the card there. But if you are using the magnetic pattern on the back side of the card, you have to move it quickly. So why it is necessary to move it quickly? We will talk about this today. And here we see very common example. This part is present more or less in every car, okay? So this is an alternator, which is a generator of electric power in a car and is a major component of the vehicle's charging system. So what is the working principle of this alternators within the cars? All these machines, instruments are related to the electromagnetic induction. We will talk about the details of the working principles of that machines. So now let's start with the induction experiments, and then I will go to the Faraday's law. During 1830s, just 200 years ago, many scientists did several experiments with magnetically induced EMFs. So these are called as induction experiments. Here I will show you few examples in order to understand the mechanism. Here we have a magnet. This is the N pole of the permanent magnet. This is the S pole. And here we have a coil. You see, there is no current at the coil at the beginning, okay? And we just connect a meter, galvanometer, let's say, to the each end of the coil, and meter shows 0 current because there is nothing inside. Just put a permanent magnet close to the coil here and wait there. So the magnet is stationary close to the coil and there is no current within the coil. But if we move the magnet up or down, okay, toward the coil or away from the coil, the meter shows current in the circuit. What do you see here? There is a current in the coil. At the beginning, there was nothing, but if I move it up and down close to the coil or move it away from the coil, then we have current in the circuit, in the coil. So this is called as induced current, and the corresponding EMF required to cause this current is called an induced EMF. Just by the movement of that permanent magnet close to the coil. So what is the reason for that? We will investigate this phenomenon today. So another type of experiment. Here we have one coil, okay? And then this coil is connected to the battery. Then there is a current within the coil. So you can imagine that there is a magnetic field produced by the coil, okay? And again, there is nothing in that coil. Let's consider this is first coil, this is second coil. We have a current and magnetic field in the second coil at the beginning. And at the beginning, we have nothing here. So just take this coil close to the first coil and keep it stationary here. So you don't move it, okay? So again, the current will be 0. But whenever you start to move that second coil up or down, then there will be current also in the first coil here. Another experiment. This is the last one. Again, we have first coil here, which is stationary, and there is no current within that coil. And then we have second coil, which is connected to the battery. So you can consider that there's a current in the coil and magnetic field produced by the coil, okay? And here we have a switch. So you open and close that switch. So what is the meaning of that? You have magnetic field and you don't have magnetic field. You have magnetic field, you don't have magnetic field because you have current and you don't have current by manipulating the switch here. So due to that manipulation, you change the magnetic field within the second coil and then you produce current in the first coil. So now we have current. So all this results are called as induced EMF or electromagnetic induction or back EMF, okay? Do you have any question with that 4 examples and experiments? So now let's continue with another type of experiment. Here we have a coil in a magnetic field. This is the magnetic field source. This is the N pole of the magnet. This is the S pole of the magnet. And here we have a coil, okay? And both ends of the coil are connected to the emitter here, ammeter or galvanometer, let's say, okay? And here we have a coil with some N number of turns. And we have magnetic field lines from N pole to the S pole within the electromagnet. Let's consider that this magnetic field is uniform in every part of the electromagnet gap, and we don't change the size of the coil. We don't change the number of the turns in the coil, then the current will be 0 within that coil. But whenever you change the magnetic field, you decrease the magnetic field or you increase the magnetic field, or you change the position of the coil, now it is staying like this, if you move it like this, then if you decrease or increase number of the turns, then a current is induced within that coil. If we change any factors here, shape, magnetic field, location, orientation of the coil, okay, if you change them, or if you change the magnetic field, there will be current within the meter here. So now maybe a little bit go into detail what is happening here. If you have a permanent magnet, then we have magnetic field lines from N pole to S pole. Okay. So if you make close that permanent magnet to the coil, if you move it toward the coil, then the magnetic field here will increase due to movement of the permanent magnet to that direction. So here we have, if you keep the permanent magnet at that point, this coil feels some certain magnetic field, but if you move it further toward the coil, it will feel more magnetic field. Or if you move it to the opposite direction, away from the coil, then the magnetic field here will be decreased. Again here, if you apply current to the second coil here, there will be magnetic field. Okay, we have discussed all these things during the previous lectures, and there will be magnetic field lines around the coil. Then you will have magnetic field somewhere here, okay? And if you move that coil toward the first coil here, then you will change the magnetic field in that direction. If you move this coil away from the first coil, then you will decrease the magnetic field. So this change in the magnetic field around the coils produces change in the magnetic flux. Then this produces back EMF or induced current within the loops. This is the main mechanism also here. So now let's try to remember the magnetic flux. Actually, we have seen this topic in chapter 27. So here we have a surface, and we choose very small surface element dA, and we have magnetic field lines like this, okay? And we have two components of magnetic field lines. One is parallel component to the surface, and the other one is perpendicular component to the surface element dA. And the magnetic flux through that very small surface element is given by perpendicular component of the magnetic field times the area. We have done it during the last lecture. This is the magnetic flux phi b here. Then let's try to remember the magnetic flux as a function of the surface. Here we have a plate you can consider, okay? And here we have the same one, we have the same one. So this is the direction of the magnetic field. Direction of the magnetic field is fixed. We change the angle between the magnetic field and the surface vector of that surface element, you can see. So now what is the change in the magnetic flux? Magnetic flux is given by B times A. This is scalar dot. You can also write like this. Let me use the pen. Magnetic flux. B times area times the cosine of the angle in between. Okay. So here, this is the direction of the magnetic field. This is the direction of the surface. Then the angle between magnetic field and the surface vector is 0. Then cosine 0 is 1. Then the magnetic flux is given by B times A. If the surface is staying like this. If I change the position of the surface with that angle, now we have phi angle between magnetic field and surface vector, then the flux is given by BA times cosine phi. And the magnetic flux is between 0 and BA. This is the maximum value, BA. And if you make the magnetic field perpendicular to the surface vector, okay, or field lines are in the surface, then phi angle between magnetic field lines and the surface vector will be 90 degrees, and cosine 90 is 0, then magnetic flux will be 0. So here we have maximum flux, which is given by BA. Here we have minimum flux, you can consider, okay? And here we have in between, which is given by BA times cosine phi. So this is the information on the magnetic flux, which we have seen in chapter 27. And now let's try to get the EMF as a function of the change in the magnetic flux. What do you see here? The area of that element is same, A, okay? Area is same here, A, area is same. But the angle of phi between magnetic field and surface vector changes, okay? Then here, magnetic flux changes, okay? So magnetic flux changes by changing the phi here. Or if you decrease the size of the area, or if you decrease the magnetic field, or if you increase the magnetic field, if you increase the area, then magnetic flux will be changed again, okay? So this is happening. So magnetic flux is changing when you move that coil. Here, magnetic flux is changing when you move that permanent magnet, okay? So what happens when the magnetic flux changes? This gives us the Faraday's law. When the magnetic flux through a single loop changes with time, there is an induced EMF that can drive a current around the loop, okay? So if you change the magnetic flux through that coil, then there will be current, induced EMF and induced current within that loop. So which is given by that expression, induced EMF in a closed loop is given by epsilon, which is equal to minus the time rate of change of magnetic flux through the loop. So magnetic flux changes. And again, from the chapter 27, remember that the unit of magnetic flux, the unit of phi b is given by Weber, okay? And we have already done that 1 Tesla times meter square gives us 1 Weber. And here, look at the unit of EMF. EMF is given in volt. We have done it in several chapters before. So volt, then here we have Weber and here we have second. So this is the unit of the EMF. So here we have many coils, but this Faraday's law gives the induced EMF in a single closed loop, okay? But what happens if we have many loops like this? Then the total EMF in the coil is given by that expression. We just multiply by n. And is the number of the identical turns within the coil, if the flux varies at time rate through each turn. Do you have any question up to that part? If you go back with that information, okay, if you go back with that information, so let's see what is happening here. Let me use the pen. Now we know that if the magnetic flux changes, then we have EMF within that system, and then there is an induced current. So let's consider that there are magnetic field lines like this, from N to S, okay? We have already done it in several chapters. So when you move this one toward the coil or away from the coil, then the magnetic flux will be changed. Okay, we know that if we are close to the poles, we have higher flux. Okay, if we are far away from the poles of the magnetic flux decreases. Okay, so by using that information, you can understand the formation of EMF in that system. If you move it away from the coil, then the flux decreases. Then we have a change in the flux by time. Then we have EMF in the coil, and there is an induced current. Then we see a current here. Do you have any question? Okay, then let me continue. Here we have one example. Magnetic field between the poles of electromagnet is uniform at any time, but its magnitude is increasing at the rate of 0.02 Tesla per second. Here we have an electromagnet. This is N pole of the electromagnet. This is S pole of the electromagnet. And there is a magnetic field in between. And this magnetic field is not constant. It is increasing, okay? It is increasing by time. Then there is a conducting loop. Both ends of the loop are connected to the emitter, okay? And the area of the conducting loop is given 120 square centimeter. And we have wires to the conducting loop, and wire again here, conducting loop, and here we have wire. So the total resistance in circuit and meter, okay, is 5 ohm, the total resistance here and also here, which is given by 5 ohm. Then what is the question? Find the induced EMF and the induced current in the circuit. Since the magnetic field increases, magnetic flux through that area will change. So like this. Look at this one. So what is magnetic flux? Magnetic flux is given by B times A times cosine. So what is the cosine phi here in that case? This is the direction of the magnetic field. This is the direction of the surface vector, okay? And the angle is 0 in between, then cosine 0 is 1. Then the magnetic flux here between N and magnetic flux through that area is given by B times A, okay? A is known, but what about B? B is given by that expression, okay? It is increasing by time. So just put that magnetic flux here within that equation. And here we have, instead of magnetic flux, put this BA. And what we have here, we can write like this, dB over dt, and dB over dt is given because magnetic flux changes by time. It is increasing, okay? And area is known. dB over dt is also known, which is given in the question. Just put it there so you can calculate the EMF, 0.24 millivolt. And then what is the induced current in the circuit? There will be current and what the meter reads. So current is given by EMF over R. You know this one from the previous chapters, okay? We have calculated the EMF, put it there. We know the total resistance of the system, 5 ohm, put it there. Then finally we have that current, 0.048 milliamp. In the circuit we have some certain current, induced current, just by changing the magnetic field between the poles. Okay, so the second question, if the loop is replaced by one made of an insulator, here we have a conducting loop. Instead of conducting loop, just use an insulating loop, okay? Then what about the induced EMF and induced current? Induced EMF will be same, okay? But what about the current? Since the current is given by EMF over R, and what we have in insulators. In insulators, we have very huge resistance, okay? Since resistance is increasing, then the current in the loop will decrease if you use an insulating wire. Do you have any question with that part? Okay, then let's continue with the determining the direction of the induced EMF. So what is the direction of the EMF, in that direction or in opposite direction? Here we have 4 conditions. I will show you 4 of them. Here we have a loop, okay? This is the area vector. This is the direction of the magnetic field. And here, this one, at the beginning, we have magnetic field like this. This is the magnitude of the magnetic field, but the magnetic field increases by time. You see, like this one, magnetic field increases by time. So then how to find the EMF produced in the loop? If the magnetic field is constant, flux is constant, then there is no EMF in the system. But since the magnetic field changes, flux changes, then we should have EMF in the system, right? So how to calculate or how to determine the direction of the EMF? First of all, just look at the flux. Flux is positive or negative. How to get the flux? Flux is given by that expression, B times A times cosine phi. This is the B, this is the A, this is the angle phi in between, okay? If the phi is between 0 and 90 degrees, then cosine phi will give us positive number, then the flux will be positive, okay? If we have this phi angle. If you have positive flux, and if it is getting more positive, okay, because B is increasing, this was a positive number, B is increasing and it gets more positive, then the change in the flux is positive. Then here we have, look at this one, we have a positive number, here we have a negative sign, and then the EMF is negative, okay? If the EMF is negative, then how to determine the direction of the EMF? You will use your right hand, okay? The direction of the thumb will show the direction of the surface vector A, okay? If the EMF is positive, then your forefingers will show the direction of the EMF. If the EMF is negative, then the direction of the EMF is opposite to the direction of the forefingers. Okay, this is the direction of the EMF, how you can determine it by using right hand. Now let's have a look at the second situation. Here we have again flux given with that expression. B is this one, A is this one, and we have phi angle between 0 and 90 degrees. Then cosine phi will be positive, then flux is positive. But what about the change in the flux? B decreasing, okay? At the beginning, it had that value. Now we have this value, okay? So the flux becoming less positive because V decreases, then the change in the flux is negative because it becomes less positive. Then here you have a negative number, here you have a negative sign, then the EMF is positive here. Then what about the direction? Since the EMF is positive, then the direction of the EMF is shown by the direction of the forefingers, okay, by using right hand. This is the direction of the surface. Now, the third one. Here, we have phi angle between A and B, and B has certain magnitude, and it is increasing, okay, you see. So what about the cosine phi in that range? Cosine phi in that range is negative, then magnetic flux is negative, okay? We have a negative magnetic flux, and then it becomes more negative because B increases. Then the change in the magnetic flux is negative. Put the negative number here, negative sign here, then the EMF will be positive. Then this is the direction of the EMF. Then the last one, we have magnetic field in that direction, but the magnetic field decreases. So what is the flux? It is negative or positive. So we can understand by looking at that angle. The angle between A and B is given by that one, and then cosine phi is negative for that angle bigger than 90 degrees, between 90 and 180 degrees. Then the flux is negative, okay, due to that condition. So B is not constant, B is decreasing, okay? Then this is not constant. So we have change in the magnetic flux due to the changing B. So what is the change, positive or negative? The cosine phi is negative, okay? Then the flux is negative. And what about B? B decreases. For this reason, this flux decreases, okay? But at the beginning it was negative. At the end it is again negative, but it is less negative because B is decreased. So for this reason, we have the change in the magnetic flux given by a positive number. Here we have positive number and then negative sign here. Then the EMF will be negative. Then the direction of the EMF will be like this. This was the fourth example. And now let's continue with the magnitude and direction of an induced EMF. Here we have a coil. You see from the cross section, let's consider that you have such coil here between two poles. This is an electromagnet, let's consider, or permanent magnet. This is N pole, this is the S pole, and we have homogeneous uniform magnetic field lines. Let's consider at the beginning, okay? And then what is happening? A 500 loop circular wire coil with radius 4 centimeter. So this is the radius of the coil, okay? And is placed between the poles of a large electromagnet. This is the electromagnet we have already said. The magnetic field is uniform and makes an angle of 60 degrees with the plane of the coil. So this is the plane of the coil. Okay, you can consider like this. And this is the direction of the magnetic field. So between the direction of the magnetic field and plane of the coil, we have 60 degrees. But what about the axis in the center of the coil? According to the axis in the center of the coil, we have 30 degrees between surface vector and magnetic field, okay? Then the magnetic field is uniform, but it decreases at 0.2 Tesla per second. So we have a changing or decreasing magnetic field. What are the magnitude and direction of the induced EMF? So look at the flux here. Magnetic flux is given by that expression. So what is the angle between B and A? This is the direction of the B. This is the direction of the A, okay? Along the axis in the center of the coil, you can consider this is 30 degrees. And then we have that flux. And what about the change in the flux? Magnetic field changes. It is not constant. So flux will be changed. Then the change in the flux can be written like this. Just put this flux here into that equation. Then here we will have dB over dt times area times cosine phi. This is constant, area is constant, but magnetic field changes with this one, okay? Then into the EMF equation, put minus number of turns. We have 500 loops, okay, in the coil. Then we have the time rate of the magnetic flux, which is given by dB, the time rate of the magnetic field times A times cosine phi. So we already know this one. Put it there, 0.2 Tesla per second, okay? And then here we have 500 turns. And what else? We have the area here and cosine phi. Then we find the EMF 0.435 volt, you can say, okay? So the positive answer means that when you point your right thumb in the direction area vector, okay, like this, this is showing the area vector as we have defined in the previous transparencies. And then the direction of the current will be like this. Induced current or induced EMF will be like this. Now let's have a look. Another example, a simple alternator, okay, this one's in the cars, or large alternators in electric power plants. They will talk about the working principle of the alternators. Here we have a picture, a device that generates an EMF. A rectangular loop is rotated with constant angular speed about the axis shown. So here we have a rectangular loop, you see, rectangular loop. And here we have brush touches to the slip ring here. We have another brush touches to slip ring here. And we have a circuit like this. we have magnetic field in that direction shown by B, and this is the surface vector of that loop, and this is the angular speed of the loop, because the loop is rotating like this. Okay, so determine the induced EMF. We have a magnetic field, and within the magnetic field we are rotating that loop. And what is induced EMF between A and B points? This is the question. Again, the flux is given by B times A times cosine phi. But B is constant here, A is constant, but phi angle changes as a function of rotation, okay? Phi angle changes, then cosine phi changes, then we have a changing flux. So this will produce EMF. So what is phi? We can write phi angle like this, omega times t, okay? Just put that phi here. This is the flux, BA cosine phi. Instead of phi, put omega t, and we have here BA cosine omega t. And then EMF is given by time rate of the flux, magnetic flux. Put the magnetic flux here. If you take derivative as a function of the time, then we will get this one, omega BA sinus omega t. So what it tells, EMF varies sinusoidally, okay? So by time. Look at this one. This is very nice figure. You can understand the mechanism, okay? Just try to concentrate. If something is not clear, please let me know. This is the time, okay? And then this is the magnetic flux, this one. Magnetic flux. Magnetic flux changes. Why? Because phi angle, then cosine phi changes. Okay? Here, magnetic flux changes with that term, cosine omega t. By time, it changes. So, good. Then what about the EMF here? Due to the change of the magnetic flux, EMF changes with sinus omega t. Then we have here a sinusoidal behavior in the EMF due to the change in the magnetic flux. So now let's look at the position of the loop here. Let me choose pen. This loop you see from end on, okay? You can consider like this. This is the direction of the magnetic field from left to the right, okay? Here, when the time is 0, loop is staying like this. Okay, this is the direction of the magnetic field. Okay, after certain time, the loop is staying like this. And after certain time, the loop becomes like this. After certain time, the loop becomes like this. After certain time, the loop becomes like this, and it goes, okay? So you rotate the loop, then the angle between magnetic field and surface vector changes. So then, as a function of that change, we have a changing EMF. You see? This EMF is given by that expression. So now, since EMF varies sinusoidally, the current that results in the circuit is an alternating current. that also varies sinusoidally in magnitude and direction. So by using this type of alternator, we produce an alternating current here. AC current you can produce by using this design. And the amplitude of the EMF can be increased by increasing the rotation speed. Look at the EMF formula. It depends on the rotation speed. It depends on the magnetic field. It depends on the area of the loop, right? So then you can increase the amplitude of the EMF by increasing the rotation speed or by increasing the field magnitude applied, or you can increase the loop area. You can use bigger loop, or you can increase number of the loops. Here we have just one loop. If you increase the number of the loops, you can also increase the EMF. So here you see a very large commercial alternator used in electric power plants to produce electricity, to produce AC electricity. And here we have another type of alternator used in the cars to produce electricity. So alternators are used in automobiles to generate the currents in the ignition, the lights, and the entertainment system. But the working is a little bit different. What we have here within that example, we have a loop, okay? We have a magnetic field, and we rotate the loop, okay? Magnetic field is fixed. But in the cars and also larger alternators in electric power plants, the loop is fixed. The loop is fixed, but the direction of the magnetic field is changed, okay? Then again, phi angle is changed. Then you can produce magnetic flux changing by time. So rather than having a rotating loop in a magnetic field, the loop stays fixed and electromagnet rotates here in the center, and there's an electromagnet, okay? So this rotation is provided by a mechanical connection between the alternator and the engine. So there's a connection between the alternator and the engine. Here we have an electromagnet in the center you can consider, okay? And here we have many loops, here you see. And here we have electromagnet. So this electromagnet rotates, and then the direction of the B changes by time. So magnitude of the B is constant, but the phi angle changes if you rotate the electromagnet in the center. So the mechanism is also same in the larger alternators used in the electric power plants. Here in the center, which is not shown here, there is a huge electromagnet, and then it is rotated, and then phi angle changes by time. Then we have changing magnetic flux. This induces EMF in the loops. Since we have many loops here, you can produce huge EMF and huge EMF currents. Do you have any question with that part? Okay, then let's continue with a DC generator and back EMF in a motor. Here we have shown that we have an alternating current we produce within the loop here, okay? Because EMF changes sinusoidally, right? You can see it here. But we have also generators or alternators. They produce DC EMF and DC currents. So how to do that? DC generator that produces an EMF that always has the same sign. Look at this one. Here in the previous case, in an AC generator, here we have EMF, and the sign of EMF is positive here and it goes to negative, okay? But in case of DC generators, the sign is always positive, okay? The arrangement of split rings here we have half ring, here we have another half ring. They are called as split rings, called a commutator, reverses the connections to the external circuit at angular positions at which the EMF reverses. We have discussed this one during the previous lectures in electric motors, okay? So in order to keep the current always in the same direction, we have such design. You can check the previous lecture notes. So with that design, with the help of the commutator here, we can always produce EMF in the same direction, okay? So commercial DC generators have a larger number of the coils and commutator segments. In addition to that, smoothing out the bumps in the EMF so that the terminal voltage is not only one directional, but also practically constant. So what you see here, EMF is oscillating, right? It is always positive, but oscillating. So, but you need a constant EMF, let's say, which is not oscillating, then you have to use some smoothing things in the EMF, okay? So commercial ones do this. So now, what is the question? Let's come to the question. Let's come to produce the EMF. Consider a motor with a square like this, 500 turn coil and 10 centimeter on a side, okay? If the magnetic field has magnitude 0.2 Tesla, at what rotation speed the average back EMF of the motor equal to 112 volt? So we would like to produce 112 volt EMF, okay? So speed of the loop is asked. So what is this angular speed or rotation speed? So B is constant, okay? The area of the loop is also constant. Only phi angle changes by rotation. So we have already calculated EMF for that condition, but here we have n number of turns. Then we have n times omega BA sinus omega t. I mean, we have calculated this one here. So then, but if you keep it like this, the EMF will oscillate by time, okay? But I don't want this. Here I have only EMF on the positive side, okay? Then what to do? To find the average back EMF, we must replace sinus omega t by its average value. We find this by integrating sinus omega t over half a cycle, okay? Just for this part. And then you can find this one, average sinus omega t 2 over pi. I will not go into detail. So just take this 2 over pi, put instead of sinus omega t. Then here we have average EMF, average back EMF, okay? You can see like this. So what we have here, number of turns, rotation speed, and magnetic field, area, and EMF. EMF is given 112 volt, magnetic field is given, and area can be calculated by using that information. Number of turns is given, then put them into that equation. You can calculate rotation speed, which is given by 176 radian per second. So what we have here, look at this one. The average back EMF is directly proportional to the rotation speed. You see, if you increase the rotation speed, then EMF increases. If you decrease the rotation speed, EMF decreases. What happens? Back EMF decreases in electric motors. We have discussed this one in the previous lectures. If the rotation speed decreases, then a lot of current will be driven by the external EMF source to the motor, then motor can be burned out. So this also gives that information. Any question here? Okay. Then let me continue with another type of generator, the slidewire generator. So what is slidewire generator? Here you see within that figure, there is a U-shaped conductor in a uniform magnetic field. We have magnetic field into the page, okay? And then we have a conductor. We lay a metal rod, this one, this metal rod here. The name is slidewire with length L across two arms of the conductor. One arm is this one, the other one is one. Then put slidewire here. And then we have a circuit, complete circuit, okay, by using that wire. Then, but okay, there is no current at the beginning. I just complete the circuit. Then I move that slidewire to the right side with some constant velocity. Okay, this induces an EMF and a current. For this reason, it is called as slidewire generator. So the question asks that what is the magnitude and direction of the resulting induced EMF? So magnetic field is constant here, but what is changing? The changing parameter is the area. Look at this one. At the beginning, the area of the loop is given by that area, right? When I move that slidewire to the right side, then I have bigger area. Then area changes by time, okay? This area can be calculated by V times dt times L, length of the slidewire. This is the increased area. So magnetic flux is given by that expression. B is constant, but A changes, then magnetic flux changes. Good. Then what is the angle between B and A? Since B and A point in the same direction, so this is the direction of the B into the page. This is the direction of the area into the page. You can select like this. Then the angle in between is 0. Then cosine 0 is 1. Then flux will be given by B times area. So what is EMF? Put flux here and take time derivative of it. Then here we have dA over dt. So indeed, the area changes by time. So what is dA? dA is given by L times V times dt. L times V times dt. This is the dA area, this area. And then put that dA here. So finally, we have EMF produced by slidewire is given by minus BLV. This is the magnetic field, this is the length of the slide wire, and this is the velocity. The minus sign tells us that the EMF is directed counterclockwise. In that direction, a current will be produced due to movement of the slide wire to the right side. Okay, now we have another example, work and power in slide wire generator. In the slide wire generator here, energy is dissipated in the circuit owing to its resistance, because this circuit has certain resistance which is given by R. Then what is the question? Find the rate at which energy is dissipated in the circuit. This one asked, okay, dissipated, and energy at rate dissipated in the circuit, which is given by that expression. And then find the rate at which work must be done to move the rod through the magnetic field. So what we have here, if we move that slide wire to the right side, then there will be a current, induced current, okay, due to the back EMF. So this is the direction of the current. By using that rule, magnetic force rule, I L times B, this is the direction of the L, this is the direction of the magnetic field into the page, there will be a force, okay, fighting against the pulling in that direction, okay? So now this will be helpful for us. So I would like to calculate dissipated power, okay, which is given by I square R. I know the R, but what is I? From this one, I know that the produced EMF within the system is given by minus BLV. EMF is equal to minus BLV, and the current due to that EMF is EMF over R. Then I can calculate the current like this. So put the current here instead of that expression, and then finally we can calculate the dissipated power due to the resistance is given by that expression. Okay, the force does work, this force does work at rate P applied, which is given by F times V. You can consider it like this: work is given by F times X. If you divide by time, or if you take time rate, then you will get power and you will get the velocity on the right side, okay? Then the power applied can be found F times V. So what is F? F is given by I times L times B. I is given by that expression. Put I here, then F is given. Put this F here, and here we have V, then another V here, we will have V square. So what do you see here? The applied force has the same magnitude and does work at the rate like this. Dissipated power, applied power are equal to each other. Okay, do you have any question here in that part? Then let me continue. This is a bio application of induced currents, induced EMFs, exploring the brain with induced EMFs. So what we have here, there is a method which is called as transcranial magnetic stimulation. Is a technique for studying the function of various parts of the brain. You can consider in Turkish beyindeki bazı bölgelerin manyetik alanla uyarılması gibi düşünebilirsiniz. Okay, what we have here, a coil held to the subject's head carries a varying electric current. This varying electric current produces a varying magnetic field. Okay, we have varying magnetic flux. This field causes an induced EMF, and that triggers electric activity in the region of the brain underneath the coil. By observing how the TMS subject responds, a physician can test for various neurological conditions. For example, which muscle move as a result of stimulating a certain part of the brain. This is bio application of EMF, induced EMF. Now let's continue with the Lenz law. What is Lenz law? Lenz law is a convenient method for determining the direction of an induced current or induced EMF. So we have learned how to determine the direction of the induced EMF here. Lenz law provides another method. It is considered simple compared to the other case. So how to apply this one? The direction of any magnetic induction effect is such as to oppose the cause of the effect. So the system, you can consider like this. The system will fight against the change in the system, okay? So here we have a coil, and then there is a uniform magnetic field, which is given by that one. If you increase the magnetic field in that direction, okay? So at the beginning it was like this, and there is no current, there is no EMF in the loop. But if you change the magnetic field, if you increase the magnetic field, the system will produce, the coil will produce an opposite magnetic field, okay, equal to the change. So what we have here, this is the magnetic flux at the beginning, B, but we increase the B. So flux changes by time, then there is an induced current in the system. What about the direction of the current? Direction of the current or direction of the EMF is determined with the direction of the induced magnetic field. The magnitude of the field is increasing, so there is an induced EMF driving a current as shown. Let's continue with the Lenz law and the direction of induced current, induced EMF. How to determine it. We will see 4 conditions. 2 of them are given here, and 2 of them are given in the next transparency. So please try to concentrate. If you understand the basics, you can keep this information in your mind. Here we have a loop, okay? At the beginning, there is no current in the loop. And here we have a permanent magnet. We know that permanent magnets have magnetic field lines from N to S. Okay, let's consider that there is very small distance between N pole and this loop. So there will be magnetic field line. Okay, magnetic field lines will be like this. What we know that close to the poles of the magnets, we have bigger magnetic field, okay? Because we have many magnetic field lines around the poles of the magnets. So at the beginning, this magnet is fixed at that position. And here we have a loop, no current in the loop. So there is certain magnetic field, but magnetic field is constant, area is constant, the position of the magnet is constant, so there is no current in the loop. Whenever we move that magnet toward the loop, okay, in that direction, what will happen? We will increase the magnetic field in that direction, okay, because we are getting closer to the end pole of the system. Normally the magnetic field produced by end pole is like this. Let me draw. This is the direction of the magnetic field, let's say, okay. You can consider like this. These are the field lines from N to S. These are the field lines. But let's consider you produce such magnetic field. If you move the magnet toward the loop, the magnetic field in that direction will increase, okay, in that area. So you will increase the magnetic flux, okay? Magnetic flux through that area will be increased. So since the magnetic flux is increasing in that direction, then this system produces an induced magnetic field, which is opposite to that magnetic field. So by applying right-hand rule, you can calculate the direction of the current and direction of the EMF. So look at the second situation. Here now we have S pole close the loop. Let me try to draw the magnetic field. So this is the direction of the magnetic field. You can consider like this. Okay. So due to the magnetic field produced by the S pole, we have magnetic flux like this through that area of the loop. And if we move the magnet away from the loop in that direction, the magnitude of the flux will be decreased, okay? If the flux is decreased in upward direction, then B is induced in upward direction. Then according to the right-hand rule, again, we have current in the loop, induced current due to the induced EMF. So now let's have a look the other two conditions. Again, here we have magnet. This is the end pole, and we have magnetic field in that direction and magnetic flux like this through that area. So if we move this magnet away from the loop, then the magnetic field will be decreased. Okay, then the induced magnetic field will be in that direction to compensate that decrease in the magnetic flux. So with the direction of the magnetic field, I can get the direction of the current or direction of the EMF in the system. So again, the same mechanism. Here we have again permanent magnet. We have magnetic field in that direction. So we have magnetic flux, okay, like this. If we move the permanent magnet in that direction, what will happen? The magnetic flux or magnetic field will be increased in upward direction. Then in order to compensate that increase, there will be an induced magnetic field in the opposite direction. So depending on the direction of the magnetic field, by using the right-hand rule, there will be an induced EMF and induced current in the system. So these are the 4 conditions in order to determine the direction of the EMF and direction of the current in the loop. Do you have any question? Actually, we have already determined the direction of the EMF and direction of the loop by using that 2 formula. This is the magnetic flux, this is the change in the magnetic flux, okay? But by applying that rules, you can calculate the direction of the EMF, direction of the current in the loop. But Lenz law gives another approach or method to calculate the induced EMF, the direction of the induced EMF and direction of the induced current in the system. So with that one, I will finish my lecture today, then I will close the session. So on Saturday, you have an exam. So please try to solve the questions at the end of the chapters. It will be very helpful for you. See you then. Take care of yourself.